US Physics Olympiad year 2019 USAPHO final round. Problem B2. Stellar black box. Scientists have recently detected a new star, the MAR Kappa. The star is almost a perfect black body, and its measured light spectrum is shown here. The total measured light intensity from MAR Kappa is 1.12 multiplied by 10 power negative 8 watt per square meter. The mass of MAR Kappa is estimated to be 3.5 by 10 power 30 kilogram. It is stationary relative to the Sun. You may find the Stefan-Boltzmann law useful, which states the power emitted by a black body with the area A is sigma A T power 4. Question A. The spectrum of wavelengths lambda emitted from a black body only depend on H, C, K, B, lambda and T. Given that the Sun has a surface temperature of 5778 Kelvin and peak emission at 500 nanometers, what is the approximate surface temperature of MAR Kappa? Question B. The lines in the spectrum result from atoms in the star absorbing specific wavelengths of the emitted light. One contribution to the width of the spectral lines in the Doppler shift associated with the thermal motion of the atoms in the star. The spectral line at lambda equal 389 nanometers is due to helium. Estimate to within an order of magnitude the thermal broadening delta lambda of this line. The mass of a helium atom is 6.65 by 10 power negative 27 kilogram. Question C. Over the course of a year, MAR Kappa appears to oscillate between two positions in the background night sky, which are an angular distance 1.6 by 10 power negative 6 radians apart. How far away is MAR Kappa? Assume that MAR Kappa lies in the same plane as the Earth's orbit, which is circular with a radius 1.5 by 10 power 11 meters. Question D. What is the radius of MAR Kappa? Over the course of some time, you observe that the star's intensity periodically dips from I to 1 minus 10 power negative 5 I, and then rises back to I with a period T. One possible explanation for this observation is that exoplanet is orbiting the star and blocking the starlight for some time. Question E. Estimate the exoplanet's radius, assuming that it is much closer to the star than to the Earth. Question F. Assume the exoplanet is a black body with a uniform temperature in a circular orbit around the star. What must T be so that the planet has a temperature of 250 Kelvin? If this were true and the planet had an appropriate atmosphere, the temperature would increase enough to support life. Solution for problem B2. Question A. By dimensional analysis, we have two energy scales. One is h nu, which is equal hc over lambda, and other is kb t. So from here we can find that these two energies must be proportional to each other. It means that lambda maximum must be back proportional to temperature. So from here we have equation this one, or T star equal this one. Because using this graph we see that maximum lambda will be around 360 nanometers. And final result is about 8030 kelvins. That was solution for question A. Also, this result could be done using so-called Wien's displacement law, which states that the blackbody radiation curve for different temperatures will peak at different wavelengths that are inversely proportional to the temperature. The shift of that peak is a direct consequence of the Planck's radiation law. Formula for Wien law looks like lambda equal b over t, where b is a constant approximately equal this one. This shift of the peak is a direct consequence of the Planck radiation law, which describes the spectral brightness or intensity of blackbody radiation as a function of wavelength at any given temperature. This is the formula for Planck radiation law. So from here we can take first derivative by lambda from this function b, and we have this equation to find. If we use hc of lambda kbt as x, we have this equation, and numerically solution give us this approximate result, for which constant b in Wien law has this meaning. So that's a precise solution which we don't need in this problem, because here we can use just dimensional analysis. Solution for question B. The root mean square velocity of the atoms in the star in the direction towards Earth is square root from kbt over m, which is about 4080 meters per second. The red shift is thus v over c is about 1.4 by 10 power negative 5, which give us delta lambda approximately equal 5.3 10 power negative 3 nanometers, which is very insignificant. That's the answer for question B. Solution for question C. This is a parallax effect as shown in the diagram. The angle Earth makes with the MAR kappa is the angular shift it makes in the night sky. Then we have that distance to star equal to distance to sun divided by theta over 2, which is 1.9 10 power 17 meters. That was a solution for question C. Solution for question D. The luminosity total power given off by the star is given by formula 4 pi d square multiplied by I, where d is distance to star and I is intensity from this star measured on Earth. But from other hand we have this total power equal surface area of star, which is 4 pi r square multiplied by sigma and multiplied by t power 4. So equalizing these two expressions, we have that radius equal this expression, which is 1.3 multiplied by 10 power 9 meters. That was the solution for question D. Solution for question E. The planet is sufficiently closer to the star that we can just take the ratio of areas. So we have radius planet square over radius star square equal 10 power negative 5, or from here radius of planet equal to 4.1 multiplied by 10 power 6 meters. That was a solution for question E. Solution for question F. Suppose the planet is r away from the star. Then the power from the star absorbed by the planet is this one. From other hand, the planet radiates the same heat with the power this one. So set them equal to each other, give us this equation, from which we can count what is the radius of orbit. That's this expression, which is 6.75 multiplied by 10 power 11 meters. Now we can recall that circular speed on this orbit equal square root from gm star over radius of orbit, or 2 pi r over period equal same thing. And from this formula we can count that total period equal this expression, which we can get from third Kepler law, and it's about 7.3 Earth years.